Hey guys, I'm Paweł and this is a regular light switch. When I switch it off, the light disappears instantly. You see, there is no delay between me switching the light off. It disappears instantly, and when I switch it on, there is no delay as well. I'll skip possible light fading caused by capacitors in model light bulbs, but essentially the action is instant. So what is electricity? In physics, electricity is defined as an ordered flow of electrons through a cross-section of examined conductive material caused by the electric field. The ordered flow means that the electrons are moving in one direction. The conductor that is used in the wall to provide the electricity to the light bulb is copper. The atomic mass of copper, which is Ma, is equal to 63.5 U. U is the unit of atomic mass. The density of copper is 8.96 gram per cubic centimeter and room temperature. For simplicity, let's round it to 9 grams per cubic centimeters. There are 2 free electrons per copper atom. Free means they are able to carry a charge. They can literally detach from an atom and move through the current forced by the electric field. So these 2 electrons can carry a charge, and in a mole of electrons, which is the Avogadro number, has charge of F equals 96,500 coulombs. This is also called the Faraday's constant. Thus, the charge of free electrons contained in a cubic centimeter of copper, meaning the density of free charge, is 9, which is the density of copper, times 2, which is the number of free electrons, times the Avogadro number, which is a 96,500, divided by the atomic mass of copper, which is 63.5. To transform it to cubic millimeter, we have to divide it by 1,000. So now it is 9 times 2 times 96.5 divided by 63.5, and this is coulombs over cubic millimeter. Let's speed things up by using a calculator. So it's 9 times 2 times 96.5 divided by 63.5. The result is 27 coulombs per cubic centimeter. 27 coulombs per cubic millimeter, not centimeter. In a copper conductor, the typical current density is 4 amps per square millimeter. So in a second, 4 coulombs of charge flows through a square millimeter of copper wire. Now let's calculate 4 coulombs of a charge moving through a current that can conduct 27 coulombs per square millimeters. This is 4 coulombs over 27 coulombs per per cubic millimeter. This equals to 1.5 of an electric charge in a cubic millimeter. This means that 3 electrons are moving 1.5 millimeter per second. If you add a salt water into a petri dish and then you add potassium permanganate crystals into it, you will see the first phenomenon called the diffusion. Let's see. So this is salt water. Let's just add a little bit of the salt water just to cover the bottom. Now I add potassium permanganate crystal into it. Just a very little bit of it, very small. It's gonna be hard. Just a little bit. No. Once more. Just a few of them. That should be enough. So what you see here is diffusion. All the purple ions are creeping in all directions. Look at this, this is fun. Now I'm going to put electric current into the petri dish using this battery. What we expect to see is another phenomena. The purple blob moves towards the anode, the positive electric charge. The speed you see now is the speed of electrons moving through the electric current. Unfortunately, it's very, very slow, so I'm gonna speed this up a little bit. Not as fast as you would expect, isn't it? Yeah, electrons move really, really slow. This is weird. It is not as fast as you would think. This is the same as moving a 1 centimeter for over a minute. This is slow. I mean, it's very slow. So what makes this almost instant reaction when flipping the light switch? With this speed, it can't possibly inform the light bulb that power is on or off. Well, this is not what is happening here. The speed of electrons doesn't actually influence how fast the information travels from one point to another. Enter the electric field. It is the thing that informs the electrons across the entire current that they should move now almost instantly. The speed of electromagnetic wave in vacuum is 300,000 km per second, and it is constant c, which is the speed of light. Thanks to its duality, the light is a particle when looking at it one way, and a wave when considering other properties. But the electromagnetic wave doesn't have the speed in a copper conductor. It's slower. Light going through a glass can slow down to about 200,000 km per hour. This brings me to an optical fiber. You see, light impulses are going through this fiber at incredible speed. The actual speed depends on something called the refractive index. It is the speed of light in vacuum divided by the speed of light in a substance. Here, this would be glass encasing the beam of light. Optical fibers have about 1.5 refractive index, which makes it about 200,000 km per second. This is the speed and information can travel through an optical fiber. That's blazing fast, but it is not the only factor that counts towards speed of information. This is the theoretical maximum speed that we can reliably send information over a distance today. It would be the speed if two computers would be directly connected to each other using an optical fiber. But this is not the case in the real world. Consider how many devices are on the way between the device you are using right now to watch this video and the server that hosts it. It is your internet provider's modem, your router, routers on the skeleton network, then the destination data center router, load balancers, and finally the server. The speed of information is limited to the slowest component of the transmission. It is not the speed of light, it is not 200,000 km per second, but it is still fast enough to get any information from any part of the world instantly. This allows us to call your family and have a decent voice connection, or downloading a video from a server located on the other side of the globe. It may feel slow sometimes, but remember that the same fiber is used by a lot of people in your area. And then again, some devices on the route to the server can cause delays in data transmission. That's it for today. If you like this video, please subscribe to the channel. Let me know in the comment section what would you like to see next. Stay safe and see you soon.